Alright, in this video we're going to we'll start with a quick review, and we're going to kind of show how what we've done is good approximations for motion, but that in reality motion is a little more interesting, okay, and a little more calculus. So let's get started. Let's start by looking at what we started with before, and we're going to make a position time graph. Okay, so if I draw a couple quick segments, you'll notice that, as we've already seen, the slope on this graph represents the object's average velocity. So, for example, in this first line segment, there's a positive slope, so the object must have positive average velocity. In the second segment, there's no slope, so it has no average velocity. And then in the last segment, there's a negative slope, and therefore it has negative average velocity. Now if we were to graph the velocities, and we can kind of go by the grid here that I provided, let's say if we count each segment by 1, that means the first break is at 5 seconds, and the second point is at 8 seconds, and it seems like the graph ends pretty close to what would be 10 seconds. So let's mark that on our velocity graph. Now if we calculate the slope, the first slope from 0 to 5 seconds, it looks pretty consistent at a kind of up 1 over 1 slope. So we're going to say that the average velocity for the first segment is at about 1 meters per second. Now you'll notice it's a fairly constant straight line, so our velocity graph should have a straight constant line at a value of 1 meters per second. The next slope has, well, the next segment on the position graph has no slope, so that would be a value of 0 on our velocity graph from 5 to 8 seconds. Then from 8 to 10 seconds we have a negative slope, and if we calculate that value, that's at about negative 1.5. Okay, and so we see that we have this segmented graph, and the problem is these dashed lines where the velocity seems to quickly drop. Okay, these are instantaneous changes. I mean, we immediately go from having a speed of, say, 1 meters per second to immediately stopping, and then from stopping, immediately having a speed in the other direction of minus 1.5 meters per second, or negative 1.5 meters per second. Physically, that's not very realistic to have instantaneous changes in speed. No matter what happens, you're going to have to slow down. There has to be a line connecting those segments, and it's definitely not going to be vertical. So here's what I mean. If we look at the position time graph again, a slightly more realistic version of what that graph should look like will have curves. Now we still see that we have generally positive slope on the left, no slope at the top, and generally negative slope on the right side. But one thing you should notice is that none of these slopes are constant. Okay? Even though they have a general straight line idea to them, they are definitely not constant. They are changing. The positive slope is gradually turning to a flat slope, or no slope, and that no slope is gradually turning to a steeper and steeper negative slope. So the slopes are, in fact, changing. Now, if we were to generalize this on the velocity graph, okay, we would say that the first slope is a positive slope, so I start with a positive velocity, but that slope is gradually flattening out. And so if I have a slope that's gradually turning to 0, my first line segment will be positive values, but those values are decreasing to 0. Now once I get to 0, no slope, okay, and I probably made this line a little too long, but I just want to emphasize that I'll have no slope for a little while, and then it immediately goes into a negative slope. And again, that negative slope starts out from having no slope, and so therefore no velocity value, and then the slope gets gradually and steeper in the negative direction. So my negative velocity value should be getting higher and higher and higher in the negative direction. So that blue line actually represents an object speeding up in the negative direction. Okay, so from this graph, and we've drawn graphs like this one before, But now we want to look at a few more ideas of what we can find from this graph. We already know that these areas underneath represent displacements. So in the first segment, it's a positive area, so that must be a positive displacement. And between the blue line and the x-axis, time axis, this would be a negative displacement. Now we can combine these and figure out the overall displacement of the object. We've done that before. The more interesting part is, what about these segments on the graph that have slope? What does it mean to have slope on a velocity time graph? Okay, well, if we calculate slope in the usual way, it's simply rise over run. Now in this case, the rise, our y-axis, is a velocity axis. So we're really looking at it 2 points on the velocity axis, v2 minus v1, over the run, which is a time axis, so t2 minus t1. Now these are generally written as change in velocity over change in time. So we have a new expression here. This is our rate of change of velocity. Okay, now that's a new one. We've done rate of change of position. That was the definition of velocity. So what do we call the rate of change of velocity? In this case, well, in general, rate of change of velocity is defined or defines what we call the acceleration. So the acceleration is basically the new idea that we're going to get out of this video. All right, so a little more to that definition. The acceleration A, describes an object's motion changes. So we define the average acceleration as simply a change in velocity over time. And then we would define an instantaneous acceleration as the time derivative of velocity. Okay, so let's look at an example. So here we have a car, and we'll say it's moving at 5 meters per second. Okay, and then later on it now has a velocity of, we'll say, 15 meters per second. And we'll say that it achieves this change in roughly 2 seconds. Okay, so if we know the change in velocity and how much time it took, we can define the average acceleration. So 15 meters per second minus 5 meters per second, all over 2 seconds. So a quick crunch of the numbers should lead to an acceleration of 5 meters per second per second. Now those units might sound kind of weird to say, meters per second per second. So let's define what that means. So first, physically, when we write it out as meters per second over a second, what we mean by this, and you already heard me say it, it means meters per second per second. So why is that important? Well, in the case of this answer, meters per second, essentially, remember, this means a change in velocity over time. So the numerator represents what's changing, and the denominator is representing what it's changing to. So in this case, 5 meters per second interprets to saying the velocity changes by 5 meters per second every second. So after 1 second, I'll have increased by a speed of 5 meters per second. The next second, I'll increase by another 5. The next second, I'll increase by another 5, and so on. So each second, my speed is increasing by 5 meters per second. Now, what do we mean when we do this mathematically? You'll see this written more often than the way I wrote it here. So this is how we're going to refer to this from now on. If you do the math of m over s, you're really dividing fractions. It's m over s divided by s over 1. So if you do a quick crunch of that, you'll get meters per second squared. So that is the way you're going to see acceleration written from now on. It's meters per second squared. But it means the same thing. It means meters per second per second. Okay, so by defining acceleration, this leads us into the bigger idea of this entire first unit. Okay, and it's called kinematics. Now, kinematics basically means the study of motion with constant acceleration. Okay, and the reason why this area of physics is really so important is because when we have constant acceleration, it takes all the guesswork out of our equations because it's the same set of equations each and every time. Okay, so it's a very defined area of physics. So let's jump right into that. So our equations, and these are equations you're going to see a bunch and you're going to probably want to try to memorize, okay, are just listed, and this is in no particular order, but they're listed as such. So the final velocity is expressed as the acceleration times the time plus the initial velocity. Now you'll notice that the symbol changed for initial. So now I wrote a 0 down. And the reason we use a 0 is because this is basically a symbol to say it's the given quantity, so in this case velocity, that's what it's attached to. It's the velocity when the time is 0, hence initial velocity. Okay, the next kinematic equation is the final position is equal to 1/2 the acceleration times the time squared plus the initial velocity times time plus the initial position. Now, you might be wondering where these equations came from, but that's going to come a little bit later in a further chapter. It involves like some calculus ideas, but basically Newton came up with these equations from something we'll learn later. Okay, so if you're curious where they come from, don't worry about that right now. Just know that these are the equations. Okay, and the third equation is really not a new one. It's basically taking these two and eliminating time, and then combining all the variables and moving stuff around. And in doing so, we come up with this last equation, and we make it a kinematic equation because we find that we do use it quite often. But there's no point in you constantly solving for t in one of these two equations and substituting into the other and doing all the algebra over and over and over again. So we define the third kinematic equation, again, combination of the previous two, as the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the displacement. And these represent your kinematic equations. All right, now let's address this idea of when we say constant acceleration, how do these three equations mean constant acceleration? Okay. So the answer to that is, well, if we start with position, so this kinematic equation, 1/2 at squared plus v initial t plus x, or the initial position. How do we find the volume, or how do we find the velocity of this? Well, velocity, remember, is the time derivative of position. All right, so what happens if we take a derivative here? So in the first term, the 1/2 and the a are constants, so we're going to bring that exponent 2 down, and that's going to cancel the 1/2, and so we're simply left with acceleration times time. Okay, in the next term, velocity times time, its derivative would just be the velocity, because that's a constant, the initial velocity, rather. And then the final term, initial position, well, that's a constant, so it goes away. Now, what do you notice about this expression? Well, that's one of our kinematic equations. So you see that we're going from the position equation to the velocity equation using the methods we know, and it gets us another kinematic equation. Now if we take another derivative, because the acceleration is the time derivative of velocity, the first term, a times t, that derivative is just going to be a. And if we take the derivative of initial velocity, that's a constant. So the derivative of the constant is 0, which means acceleration equals a, which is in fact constant. So that's what we mean by motion with constant acceleration. If we take the derivatives down to get to the acceleration, it's not a function, it's a constant value. And if we go and do antiderivatives from here, we keep ending up with the same equations over and over and over again. So that's why we call it kinematics. It's the same set of equations no matter what the problem. If it has constant acceleration, these are the equations we're going to use. Okay, so let's do a quick little outline of how we would use these equations to solve a problem. All right, so if you're problem solving with kinematics, okay, there's a couple quick steps we can get comfortable doing, especially at first. So the first would be to draw a picture. Now you'll notice that whenever I do examples, all I'm doing is drawing pictures. Okay, but typically the problems in the book are not given to you in picture form, they're given to you in word form. So you have to know how to take that and interpret it to a picture. So in the notes I always default to a car changing. So let's say that we have this car and it's in two positions because it's traveling forward. So we want to label everything. Notice that I put the initial position under where the car starts, and if I knew the value I'd put it in. The final position is where the car ends. Again, if I knew the value I'd put it there. Time, if I knew it, I'd put it, I put it in the middle just to kind of emphasize this is the time between the events. Because this is motion with constant acceleration, I also write the acceleration in the middle because it's the acceleration throughout the problem, because it's constant, doesn't change. And then the last thing would be your velocities. So I'm going to put the final velocity where the final position is, and the initial velocity where the initial position is. So I've labeled out where everything would be from the problem. And again, you should fill in numbers if you know what the numbers are. All right, the second step would be list your variables. So every variable that's in that picture, list all of them, and put a question mark for whatever variable is being asked for in the problem. Okay, so get used to writing this list. You have initial position, final position, initial velocity, and final velocity, acceleration, and time. All right, so the next step would be look at these variables, look at the list, look at what you have, and look at what you need, and then look at the three kinematic equations and figure out which equation will fit those variables. You can only solve an equation for one unknown, so you want to fit these variables and their respectable values into which equation will actually solve for you. And once you've found that equation, solve the problem. Okay, so let's do an example of this. So again, we'll have the car. We'll say it's traveling with an initial velocity of 5 meters per second. Okay, and then it ends with a velocity of, well, we don't know. Let's say that's what we're looking for. We'll say it starts at a position of 2 meters, and it ends at a position of 18 meters. We'll say it has an acceleration of 3 meters per second squared. Okay, and for the time, well, we don't know how long this took. So there's two things we're going to solve for here. So I drew my picture, now I'm listing out my variables. So I make my list, and I fill in what I know from the problem. Initial position is 2 meters. Final position is 18 meters. The initial velocity is 5 meters per second. The final velocity, I don't know, but we're looking for it. The acceleration is 3 meters per second squared. And time, we don't know, but we are going to try to find it. Okay, so from the list, we have to determine what we're going to solve for. Now there's two things to solve for, so pick one. Let's do t. So I list out an equation, so I'm just taking a guess here. It's the first kinematic equation that's listed in our equations. Well, will this equation solve for t? The equation does have a t in it, and if I look at my list, do I have everything else? I have a, I have v initial, but I don't have v final. So this equation won't work for me. So let's go on to the next one. So I write out the next kinematic equation. Now keep in mind that as you do this over and over and over again, you don't have to write out each equation. You'll probably be able to identify just by looking at the problem. But for these first few run-throughs of these things, you probably want to write them all out. So go through each one. Do we know the final x position? Yes, it's 18 meters. Do we know the acceleration? Yes. Do we know the initial velocity? Yes. Do we know the initial position? Yes. We know everything in this equation but time. So this is what we want to use. So I'm going to plug in all my numbers. Okay, so these numbers came straight from the list. Now how do we solve this for t? Well, we're going to do a quick little review step here. Okay, you'll notice that if I move the 18 to the other side, combine the like terms, I get 0 equals half times 3 is 1.5. We have 5 meters per second t, and then 2 minus 18 is negative 16 meters. So if you notice, to solve this for t, you have to identify the type of function it is. And if you remember from your math class, this is a quadratic function. So recall that quadratic in the form of 0 equals ax squared plus bx plus c. In order to solve that, you would use the quadratic equation. In this case, our variable is t, but it's negative b plus or minus the square root b squared minus 4ac all over 2a. Okay. So I'm not going to use this equation. I'm actually going to jump to a program to do this, and if you have a calculator to do it, fine. But if you need to plug it in here, then you can work it out using the quadratic formula. So I jump into this program called Mathematica, and I'm basically telling it to solve the quadratic of 1.5 t squared plus 5t minus 16. And I'm solving this for t, and when I do that, I get my two answers. We're talking about a physical problem, and we're trying to find time. So the negative answer is just not physically possible. So we know right away that the correct answer here has to be 2. So we can go back to our list of variables and add the 2 seconds in for time. Now the last thing we want to solve for is the final speed, v1. So let's go back to the equation we originally started with, because now we have everything we need to get v1. A is 3 meters per second squared. T is 2 seconds. And the initial velocity was 5 meters per second. So when we crunch this whole thing out, we get a total of 11 meters per second.